So today we are excited to have a very special speaker, Mike Fetcenko. He's the executive chairman of Sion Power today, but he's a very unique person, or a person with a unique history, I should say. He's in the battery industry for 42 years. That is quite a number, I think. And we are especially excited because we are the ECS Detroit section, and we're using these Zoom meetings to also connect to speakers that could normally not be here because they're from different locations. But this one, Mike, is really somebody who lives in the Detroit area, so he's really a local, even though he's all over the world with his business endeavors. So, but Mike Fetcenko is someone who can really close the loop in history from a material invention through all the development process to commercialization. He has seen it all. So he has contributed to active materials like nickel metal hydride with his patents, and he can look at 25 million cars on the road with his stamp on it, on his inventions in them. He used to be president of Ovonic, the company that did all the nickel metal hydride work. And then he as Ovonic was taken over by BASF, he became a director there. And he knows, and I find this really interesting, he knows every aspect of licensing and patents. So he's really an expert in that field. He just told us that he was talking to financial investor people in New York just recently. So it's somebody who really knows how things work. We were on a panel together a couple of years ago, and when we for the first time we talked a little bit more, and I realized he's the person whom I would ask if I started a startup business to consult me in business strategy. He knows how a startup runs from beginning to end. So Sion Power obviously is very lucky to have him, and so are we today. And so with no further ado, I hand over the screen and the microphone and the camera to Mike. Thanks for being here.
Thank you. Thank you, Tobias, and thank you, Eric, for the really kind invitation. I think the last one of these I attended was last year when Mike Thackeray was giving a talk, and that was really quite exciting. I like what you guys are doing very much, and hope you'll find this interesting. Maybe it's less academic than maybe is normal, but there is a lot of techie stuff in. So I hope I can appeal to the scientists and to the business people and to everybody. There's 3 sections to the talk tonight. One of them is nickel metal hydride, and you wouldn't really know that there's a connection between nickel metal hydride and NCM cathodes. And then you wouldn't know that there's a nice connection to what comes next, lithium metal anodes. That's what I'm doing now. So as Eric said at the beginning, probably I can pause for questions at each section if that's what you want to do. And I've also seen that people sometimes even on Zoom are furiously taking screen grabs, and there's nothing so exciting tonight that you might want a copy of the presentation, but if you do, I'm happy to comply. So as Tobias said, this is my 42nd year in the battery industry. I wasn't around in the 1900s when electric vehicles outnumbered internal combustion engine vehicles, but I was around in the 70s when electric cars were proposed because of the oil embargo. It didn't really fly at that time. I was around in the 90s when California Air Resources Board mandated EVs, The car companies hated EVs back then, maybe more than anything, because they were being told to do it, and it didn't fly then either. But now you have legacy automotive companies, 100-year companies like Volkswagen and General Motors, who have said, we're going to stop making internal combustion engine cars sometime in the future. It's really fantastic. They're here to stay, and car companies are all dying to compete with each other over electric vehicles. It's really, really exciting. But then even you get a really premium automobile like a BMW, like a Tesla, and customers are still not entirely satisfied. Either they're too expensive, or they don't last so long, the driving range isn't enough, or they want them to recharge faster, or the car lasts longer than the battery. And there's still a lot of work that can be done to improve electrification. So I think we're seeing something generational, a once in a lifetime event, which is the electrification of the global transportation industry. And lithium ion, it's amazing. Lithium ion was my enemy back in the 90s when I was nickel metal hydride. And there was a lot of competition and safety issues for lithium and weight for nickel metal hydride. But clearly, there has been a situation where lithium ion has become the world standard. Yet, people are now asking what comes next. What's interesting is before lithium ion and nickel metal hydride entered the market, both around 1991. So nickel metal hydride, some 1989, lithium ion, 1991. But before that, there was really no other rechargeable battery systems that had any significant commercial penetration other than lead acid or nickel cadmium. So you had a situation that the first new rechargeable batteries in 100 years were developed around the same time. And it's very interesting for me to see people touting all these brand new technologies there, but because sometimes they're just recycling what was tried and failed back in the 70s, 80s, 90s, but it's a new company and a new idea. And that's still okay, because now you can take a technology like lithium sulfur or sodium ion, and there's been material improvements where maybe they have a chance again now. First part of my talk tonight is going to focus on kind of what I know best, nickel metal hydride, back from my early days starting at energy conversion devices. So before there was Ovonic battery, there was ECD, energy conversion devices. And I think a lot of people in the local area still at BASF, Ovonic people that stayed at BASF, Subhash Dar, one of the pioneers in nickel metal hydrides, running American Battery Systems now. And so a lot of people in the area. Nickel metal hydride is really kind of an interesting technology because you're using it today and you sometimes don't even know it. If you've got low jack or some kind of what General Motors calls the OnStar kind of things, most of the time it's powered by nickel metal hydride. And one of the reasons for that, those little button cells, is that it's rugged. Nickel metal hydride is almost indestructible, but it's a versatile technology. You can go from 60 or 20 milliamp hour button cells up to 200 amp hour prismatics. What's in a Prius, what started in a Prius was a D cell. And in the Toyota Prius now, it's these 6 amp hour monoblocks. And so you can make prismatic versions of nickel metal hydride. There's a billion of these consumer AA's, AAA's. So nobody sells loose lithium ion. So if you go into the store and you're buying a rechargeable battery, no matter what brand name it is, it's probably nickel metal hydride. And one of the reasons is the safety that comes from using a water-based electrolyte. So one of the ways you can help the environment, I guess, is buy rechargeable instead of throwaway batteries. I loved this poster when Gold Peak, the Hong Kong company, came out with it. You want to replace primary alkaline, you can do it by recharging. And whatever name you buy, Duracell, they don't make, or Energizer, they don't make these nickel metal hydride. They're private labeled by some of the big companies in the world, like FDK, division of Fujitsu. Panasonic is still making most of the hybrid batteries. High Power in Shenzhen, and still Gold Peak is one of the big producers of nickel metal hydride as well. So Tobias was very kind for that introduction. Yeah, licensing. Oshinsky, Stan Oshinsky, former boss, used to say, I knew we had something really good when people tried to steal it. You never would have imagined that patents would have been such a big deal, that the patents ended up defending the technology. And it was interesting that over the course of our first licensee, which was Varta, the German battery company Varta was a licensee back in 87, 89. There ended up being 40 licenses worldwide, really everybody. Some of them were wanting to get access to the technology. Some of them had to be shown the way through, let's say, legal means. But patent enforcement ended up being a part of my job. And you can still find these. If you go into Best Buy or Walmart or whatever, and you find rechargeable nickel metal hydride, just know that the billions of cells that are made and sold each year still were invented here in Detroit. And you want to think about environment. First way to do environmental thinking is first recharge the battery, but then recycle. And why that's important is that even lead acid, a system that's been around for a while with an excellent recycle record, still some lead acid makes it into the land stream or into the landfills, makes it into the incinerators. Nickel metal hydride, we say first recharge, then recycle. But if some of them make it into the landfill or the incinerator, they're benign because there's no cadmium, no lead, no mercury. So nickel metal hydride remains an environmentally responsible chemistry. Not everybody knows this, but the word ovonic came from Stan Oshinsky, a branch of semiconductors. Stan was a prolific inventor. He was the founder of ECD and Ovonic, and Stan had over 400 patents. It's really amazing, not quite Edison 1,000 patents, but 400 is pretty impressive. And he was awarded National Inventors Hall of Fame, partially for solar, but mainly what was related to nickel metal hydride technology. So we still fondly remember. Ovonic had a huge, I'm showing this kind of history, not to focus, I'm not going to spend much time on this, but I wanted to point out in particular this USABC contract that we received in 1992. I was hunting all over my files and offices for a photo. Subhash Dar, Stan Oshinsky, Dennis Corrigan, lots and lots of my colleagues from Ovonic that we were the first USABC contract, Ovonic, for back in 92 for making nickel metal hydride into vehicles, and it was very successful. It ended up forming the GM Ovonic joint venture, which became Cobasys, which stood for Chevron Ovonic Battery Systems, and Cobasys ended up being absorbed by Robert Bosch. And so Ovonic had really a tremendous history, but more academic. I'll say we go back to, if anybody's interested, I've written papers that I said, ugh, they don't stand the test of time very well. But Stan, myself, and John Ross from Stanford, we wrote a paper back in 1993 when there was no large format nickel metal hydride. There was only AA's and C cells. We wrote a paper back in 1993 for Science, heavily refereed paper, which was promotion of the technology for electric vehicles. That article actually was pretty good. It stands the test of time. So if anybody's interested to learn more, that's a great place I would push you. And the main thing, so a lot of us at the time, I can remember telling Stan that EVs, forget EVs, let's stick with consumer. That's where the money's to be made and all that. But Stan, kind of force of his will, he was just absolutely convinced that electric vehicles would take off and we could help that happen. So this was a 6-cell D cells that was formed the original Prius and Honda hybrids. This was the 6 amp hour monoblock that's used in today's Priuses. This was the 120 amp hour prismatic block that we used for electric vehicles such as the Chrysler T-Van, but the famous GM EV1. So nickel metal hydride took the battery, the famous T-shape that was lead acid. Stan gave GM the first battery and said, hey, look, if it doesn't do what you want, forget about it. But it actually performed well. It doubled the range of the EV1. I drove this. Some of the Ovonic people were proud to get speeding tickets because that car really was ahead of its time. It didn't have the power electronics and the computer technology that we have in today's vehicles, but it was a really beautiful ride. And what a shame, you know, that documentary, Who Killed the Electric Car, I'm not going to put blame, but the Ovonic nickel metal hydride contribution to that vehicle and that whole program, back when I was a young man, you get old and a little heavier, but a lot older and a little heavier, hopefully. It was really quite exciting times. Also, if you're interested in learning more about nickel metal hydride, I can point you, there's several editions of the Handbook of Batteries where the chapters for nickel metal hydride were submitted by Detroit area people. John Koch, Kuo Young, myself were very instrumental in that. So take a look. There's just some references if you're interested. And I always love in the scientific meetings when people talk about SEI layers. You're looking at the solid electrolyte interface for nickel metal hydride. So think about over here, you've got metal with hydrogen in it. Over here in the electrolyte, you've got hydroxyl ions that want to come together. The hydrogen wants to come together with the OH from the electrolyte to form water, giving off the electricity. The problem was that the oxide barrier, the 1,000 angstrom oxide barrier, really was a barrier. And the first nickel metal hydride batteries we built for camcorders and computers and phones really were low rate only. They really couldn't handle the power needed for vehicles. This breakthrough surface, so this, when you talk about breakthrough, sometimes that's a term that's overused, but this was a surface that catalyzed that reaction. And what you're looking at then is the SEI layer, which is an oxide, but these bright spots here are metallic nickel catalysts. They're somewhere in the range 50, 70, 20 angstroms in size. And instead of the oxide being a barrier to hydrogen plus hydroxyl reaction, this SEI layer now catalyzed it. And the power levels went up by an order of magnitude. So if you want to see the before and after, here was the oxide before these catalysts were embedded, and the power levels just increased dramatically. So what I will tell you is very interesting. There are, I think it's closer to 30 million hybrid cars on the road with nickel metal hydride. It's been a big success story. I've driven Priuses for 20 years now. It's a beautiful car. You get a true 50 miles per gallon. It's not a pure electric, but the infrastructure for charging electrically is still getting off the ground. So one way to avoid that is hybrids, where you fill up with gasoline. I get a true 50 mile per gallon range. And the batteries, the Toyota people never liked this joke. When I used to go to Japan and meet with them, I would say, when are you guys going to design a car that goes as long as the battery? And they would ha-ha politely, but I don't think they really liked it. Nickel metal hydride is really an indestructible technology. The batteries do last the life of the car. You've got, if you go to New York, the taxis are all hybrid. And they've got situations where the batteries have gone 1 million miles in those kind of applications. So with that as a bridge, and say I can take questions on nickel metal hydride, but one of the things I wanted to do next was show you how nickel metal hydride led into NCM cathodes. So Eric, Tobias, I guess I'm not sure to know whether there's questions now or whether we should just keep moving. If you guys have a guidance, that would be great.
So there aren't any questions in the chat at the moment. If anyone has one, maybe we'll just pause for 30 seconds, see if anyone types it in, and if not, we can just move on to the lithium ion portion.
I can take them on the fly then too. Okay, that's thank you. So we're in a different environment now with electric vehicles. Car companies now, I mean, there's so many beautiful offerings that are coming out. Tesla obviously gets a lot of attention, I think deservedly so. The BMW products are fantastic. Locally, the General Motors and Ford offerings are, it's really an exciting time where now there's going to be as many different offerings with electric drivetrains as there have been with internal combustion engines. And it's exciting to see. I could have put pickup trucks, when I'll be talking about commercial trucks in a moment, but there's new startups like Fisker and Rivian's coming on. And I could have listed 20 different models here. But what's interesting, and the focus of my talk is going to be the cathode on the lithium ion, because I really want to make a couple points. The most expensive component in a battery right now, lithium ion battery, is the cathode. And out of the cathode, the most expensive component are the metals that go in. The nickel, the cobalt, manganese is pretty cheap, but nickel and cobalt are a bigger fraction of the cathode cost than the processing. And what that means is your choice of cathode influences energy, safety, but also cost. People are working really hard to try to get the amount of cobalt down. And taking that further, the supply chain is under tremendous pressure because of electromobility. So look at here in 2015, what you want, the takeaways you want to get here, first of all, were the number of megawatt hours, and here's what it's going to be in 2025. It's grown by a huge amount, 5 times or so, but also see why it grew. In 2015, consumer electronics was still the biggest market, but by 2025, consumer products are, now a smaller fraction. So when you think about the cathode suppliers, look at how they've had to expand. And that's how BASF got into the business, for example. I'll talk about them a little bit more in a minute. But this is what I want you to see next. So you talked about the cathode materials. It was driven by electric vehicles, but now look at the types of cathodes. And so here we were in 2019, NCM cathodes, nickel, cobalt, manganese were about half the market. Here's the projection for 2030, that it's going to be 80% of the market. Maybe LFP is beginning to make a bit more of a splash, maybe a resurgence because of cost, but also nickel availability going forward. But I want you to see that the amount of material in number of tons is incredible, and that the number of tons are mainly these nickel, cobalt, manganese style of materials. Okay, so I said there would be a bridge. How's Ovonic get involved in this? The nickel metal hydride cathode is nickel hydroxide. And it's usually nickel, cobalt, zinc for a nickel metal hydride battery. But what you want to get out of this slide is that the nickel hydroxide that you use for nickel metal hydride is essentially the precursor for today's modern NCM cathode. And many companies that are active in the NCM space originally got their precursors from Ovonic, because we were producing initially a kilogram per day, then up to a ton a day. And oftentimes we'd get these requests. So Christian Fierro, locally still, I think, was really one of the key guys on this. I'm going to talk about other key guys in a moment, but keep in mind that from 1991, when lithium ion was introduced, until really 15 years later, the primary cathode was lithium cobalt oxide, 100% cobalt, and way too expensive. But the replacements, lithium manganese oxide, lithium nickel oxide, either weren't safe or weren't stable. And the problems were that basically they wouldn't cycle. You couldn't get them to operate. So some of you were here back in July 2021 when Mike Thackeray gave a talk to the local ECS. I listened to that too, and it inspired some of the things that I'm going to talk about tonight. Mike is one of the most humble guys I've ever met. And he's one of the key guys. I think you could make the statement that without Mike Thackeray and the inventions of the Argon Lab, I don't know that electric cars would be viable right now. So, you know, this is Mike Thackeray. I think I don't need to introduce the other guys. What I want to do is, I'm showing this because at the Department of Energy and really up to the offices of the president, the work of Argon Labs on these nickel cathodes was really perceived as the enabling feature for commercially viable electric vehicles. Mike's patents, and I'm going to talk about why am I talking about Mike Thackeray's patents. I'm going to get to that in a moment. But Mike's patents solve the problem of the NCM materials not being stable. And, you know, he walks in the clouds. I'm not showing these pictures to talk about important people and key people that I'm one of them, only that I got to meet and have dinner and be friends with many of the important people. So Mike was John Goodenough's student. Stan Whittingham, I've known Stan for 25 years now. Martin Winter, one of the key electrolyte guys in the entire world. This was back in 2017. I'm going to get to that in a minute. But here is the commercial NCM cathode material. And the way I describe it to people when I was talking, we could talk to scientists and say that the second domain, one was orthogonal, one was tetragonal. The way maybe to think about why Mike's invention works is that when you over-lithiate the NCM, you create this second phase. And the way to think about the second phase is like concrete that's been reinforced, the so-called rebar kind of thing. The second phase provided a stability during the charge-discharge reactions. And how I got involved was back in 2011, when I was still at Ovonic. Mike Thackeray was asking for help. It's a little bit the way Tobias was saying it. He wanted to know, he says, everybody's using my technology, but nobody's paying. What can I do about that? And I said, well, you know, yeah, licensing and patent enforcement is not easy. One of the most interesting things that happened in the industry field that really never got a lot of attention, and this was from the Department of Energy, really choked with the idea of having the Argon key patents given to a private company. So basically what I said at BASF, so when Ovonic got bought by BASF, and I originally told Mike I couldn't help him when I was at Ovonic, when I was at BASF and they had a license for the Argon technology, my boss at the time in 2012 asked me to take a look at the Argon patents. Do we need the Argon patents, or do we need 3M? Or do we need both, or do we need neither? And it ended up being that we found out that everybody was using the Argon patents and nobody was using 3M. We ended up getting the Department of Energy and Argon to give BASF exclusive rights to the patents. And this was where I got involved then. I was enforcing the patents. Some of these companies that ended up becoming licensees weren't really doing it willingly, and they needed a little legal encouragement. But during the years 2017 and 2018, we licensed all these companies. And I would say every significant supplier of NCM cathode material in the world is a licensee of BASF and Argon. BASF is also one of the big producers of NCA cathodes. So if you buy a Tesla, you're already buying BASF cathode materials. And Mike and the guys, so in 2016, or actually it was April 2017, I got a chance to give a talk at a special award symposium for Mike Thackeray. And we didn't know it at the time, but the guy right before me was Stan Whittingham. The guy right after me was John Goodenough. At the time, we didn't know they were Nobel laureates to come. They were just Stan and John. But Claire Gray, Martin Vinter, Mike Thackeray, these are, I think, some of the key movers and shakers that have enabled practical electric vehicles, and we're in their debt. And you know, I really count it an honor to be friends with some of them. So cathode and market growth and all of that. So I already showed you what the number of tons of material, how the market is growing over time, and that it's through electromobility. But what I wanted to do was focus on this graph for a moment and talk about how the first NCM cathode cars, and there's even still some out there still today that are using NCM 111, which would be 33% nickel, 33% cobalt, 33% manganese. Because cobalt prices went crazy, it went to 622. And it's gone to 811. Some of the NCA materials are down to 3 or 4% cobalt. But the thing that you want to see is that there's a big trend for high nickel cathode materials. And the problem is, that's great. There isn't enough cobalt in the world. And so it's really good to use cobalt more efficiently. But there also is going to be a problem when we get up to these kind of tonnages in the very near future. There's not enough high purity nickel in the world. There's plenty of nickel. There's not enough high purity nickel. And the prices that are needed to open up new mines and new refining capabilities are not there yet. So when people talk about, the price for the battery is going to go down to $60 per kilowatt hour, the cathode producers sometimes go have a drink afterwards because they know that's going to be very, very difficult. But there's room for some interesting things to happen. There's a material I'd like to introduce to you. This is a BASF material, NCM 307, so 0 cobalt and 70% manganese. It's got extremely high capacity, but it's had a cycle stability problem over the years. The manganese will kind of leach out. But what I want you to see is here's the previous material from maybe 5 years ago and more recent NCM 307s. I'm not advertising this today for BASF. They can do that when they're ready. But I think that this material will become very important in the world, the same way that LFP is becoming important. Why? Because prices for nickel and cobalt, LFP is an interesting substitute. I think these high manganese materials will also become more prominent in the future. So what comes next? So my bridge was nickel metal hydride, then to NCM cathodes for lithium ion, and working closely with Argon Labs to what comes next. And you start out by saying, okay, a lot of people are working on a lot of things. I see flow batteries coming back or being promoted to come back. People are still talking about lithium air. For many years, Sion Power was working in lithium sulfur, and it's a wonderful system. And lithium sulfur, from a cost perspective and a watt hours per kilogram, is fantastic. And there's probably going to be, there's a big DOE program to go back in and look at sulfur cathodes because it's so cheap and the weight advantage. But for today, the reason lithium sulfur doesn't make sense is volumetric energy. Watt hours per liter was never very good, and cycle life. But there are pathways to address both of those. What I'm working on at Sion Power is lithium metal anode with NCM cathodes. And this is a 17 amp hour pouch cell. People talk about now, some companies, I won't mention them, but some companies, oh, we went from 1 layer to 4 layers and we're up to 10 layers now. We're at 70 layers. This is, I don't want to hear about beaker stuff and I don't want to hear about PowerPoint. We've taken these 17 amp hour pouch cells and modules, fully turnkey with BMS supplied, constraints, thermal control packs that we're giving out. Big news for our company in the last, so BASF is a shareholder since 2011 and joint development partner. But in November, just not that long ago, Cummins, the big diesel drivetrain for commercial truck company, invested in Sion Power. They also are a joint development partner, and they are also our customer outlet. And so I'll talk a little bit more about that in a moment, but you know, what is the chemistry? And so you start out by saying in a conventional lithium ion, graphite is the anode, and that's obvious. And almost everybody uses a little bit of silicon. There's a lot of companies that are touting the idea of using a lot more silicon or even pure silicon. And there's issues of the silicon with cycle life, with energy, with expansion, and everybody's got their own ideas. What Sion is doing is taking the graphite out. We scrap the graphite anode and we replace it with metallic lithium anode. Now that can be a foil, but what we're actually doing is something thinner than a foil. We're using a vapor deposited lithium film as the anode. You think about 5 microns or 10 microns lithium metal anode. And I'm going to talk a little bit more about that chemistry and why we're doing that approach in a moment, but what's the benefits of doing that? It's very interesting for me to hear companies talking about solid state for high energy. You don't get high energy from going to solid state. You get the high energy in solid state because this enables you to use lithium metal anode. So said differently, it's the lithium metal anode that provides the high energy. Some people think you can't use lithium metal anode without solid state, and we think that's wrong. The benefits, and I'll show you the data in a little bit, our first generation designs were 400 watt hour per kilogram and 800 watt hour per liter. We've got what we'll introduce for commercial trucks is 500 watt hour per kilogram. We've got aerospace designs that have gone up to 700 watt hour per kilogram. Some trade-offs there, but what I'll say is that you don't need solid state in order to get safety. I'll show you how you do get it. So let me do a comparison then of lithium ion solid state with a thicker separator that's actually loaded with lithium. So it's not necessarily a lower amount of lithium in a solid state design, and what we call Licerion. So we're using the same cathode. You can use, we're cathode agnostic. So I will say you can use LFP if you want, you can use NCA, you can use NCM. We tend to use a nickel 811 for almost all the data that I'll show you in a moment. But people want to say, what is Sion working on? It's lithium metal anode with conventional lithium ion cathode, conventional lithium ion separator, and conventional lithium ion electrolyte with a twist. We do change the formulation a little bit. Now I'm going to explain why in a moment. So here's what I mean. If you replace the graphite, the two key takeaways I want you to get from this slide are, first, if you replace the graphite anode with a metallic lithium anode, you double the energy. It's really that simple. The second key takeaway is that lithium metal anode is cathode agnostic. And so one of the things that I talk to automotive customers all the time, and everybody's interested in double the driving range. That's without question, for premium applications, but for everything. Everybody wants to go from 300 to 500 miles. That's fantastic. But another customer is interested in keeping the 300 miles he already has, but getting rid of the nickel and the cobalt. So if you look at the LFP design and you say, okay, with a metal anode, lithium metal anode, you can get 300 watt-hour per kilogram, basically the same or higher than lithium ion. So you're telling me you can give me the same range I've already got, but no nickel, no cobalt? I think there's as many people interested in that option, lighter, smaller, cheaper than the longer driving range options. And I will tell you this, I think we're very mature in our technology on nickel cathodes. We're not as mature yet on LFP, but we're working hard on it. And I will tell you that we've done 300 watt-hour per kilogram, and we've done over 500 cycles in an LFP based design. So this is very exciting, and we're bandwidth suffered. We got 100 people in our Tucson location. We're going to be expanding like crazy. So if people are interested to join Sion, you can see me afterwards about that. We are hiring. And you know, what's also interesting, people talk about, I have a design for energy and another one for fast charging. Look, one design has to do everything. So when I'm touting the benefits of nickel or of Licerion with a nickel cathode, I'm saying high energy, but I'm also going to show you some remarkable fast charge result, very safe, power levels great, cycle life is great, broad temperature range. This is, I think it's a very exciting technology. We've been very fortunate. I'm not going to talk about our board. Why are you talking about our board of directors? And only to talk about Jim Simons. Jim has been our financial backer, Euclidean Capital, now for a couple of decades. He's a world-class mathematician. Jim was the inventor of quantitative trading, and he's one of the richest guys in the world. Jim wants to see long-range, affordable electric vehicles in real people's hands. Peter Schumacher of BASF, he's the president of their $20 billion catalyst division. BASF's invested over $1 billion in lithium cathode materials. So all the battery activities are under Peter's division. So BASF has been a staunch partner for a long, long time. Cummins came on in November last year, and we couldn't be more excited. We've been quiet compared to a lot of other competitors who have had a lot more publicity. We've been quiet until we could perfect the technology. But let me talk about our initial market, which is going to be trucks. So what I want you to get, I'm only going to show this one part of this one graph is where my focus is. Passenger EVs are a huge market, but commercial EVs are going to be comparable in volume to passenger cars. And how can that be, Mike? I don't really understand. The answer is one truck uses enough battery that's equivalent to maybe 20 cars. And Cummins supplies the drivetrains for all kinds of customers. When you go down the road when you're driving on the freeway and you go by a semi truck, you don't see Cummins on the name. You see Kenworth, you see Mack, you see Peterbilt, you see Freightliner, you see all these different companies. Cummins supplies probably half of the drivetrains that go into that. And like General Motors and General Motors and Volkswagen have said, we're going to be electrifying the fleet. Cummins is doing that same thing for trucks. So class 8 vehicles, medium duty and light duty. Our relationship with Cummins is on these kind of size trucks. we are free and we are working with other companies already. We have JDAs with 2 very well-known automotive companies that we're working with. And so you'll see more from us in the future on that. So where our status. So in 2015, we had some lab cells. I had a 3-layer pouch cell. And when I hear people talking about they've gotten up to 3 and 4 layers, okay, I sort of think about, well, that's where we were in 2015. We went to 1.8 amp hour pouch cell. Now today, our size for our cell is 6 and 17 amp hour, but we also have modules. What we're going to be moving to, let me stay on this and say this is a 10 centimeter by 10 centimeter cell with about 70 layers. When we go to our 74 amp hour cell for trucks, it'll be the same number of layers, but instead of 10 by 10, we'll go to 10 by 30. So it's a footprint is how we'll go to the bigger size cells. And the motivation for our technology is first of all, high energy. We see our initial energy, the products that we're making now are 400 watt-hour per kilogram. But as we increase that footprint, when I talk to you about going from 10 by 10 to 10 by 30, the energy is going to go up to 500 watt-hour per kilogram in that design. We have aerospace designs that are even a little bit higher. Let me show you that. So we've actually demonstrated aerospace designs where cycle life is not really so important. We've got test results at 700 watt-hour per kilogram and 1400 watt-hours per liter. Now, 2 things. We don't get the power that we need in that design for EVs for high rate charge and discharge, but that's clear from the graph that I'm showing you. But what I'll tell you is that we'll also sacrifice cycle life when we go to that 700 watt-hour per kilogram design. But for rockets, drones, high altitude communication, cycle life isn't so critical. But let me speak of cycle life. Instead of, sometimes this graphic is confusing, so let me tell you that what Gen 1 and Gen 2 and Gen 3 mean. That isn't future. This was maybe 2018. This was 2020, 2021. This graph is probably already or is obsolete already. We have lab results now that are well over 2,000 cycles. What I want to tell you is that cycle life is something we've been working hard on for a long time. And I think we understand the failure modes very well. And I think this is something that's going to be an area where we continually make improvements. The one thing that's interesting is that we've also been doing the WLTP. You know, those of you in this audience tonight that are working for some of the automotive companies, you know this better than me. Basically, it's real world testing. And what we found is that our technology loves this kind of testing. So I would tell you that our cycle life is probably well in excess of what's needed under real world applications. The lab scale stuff where you do every cycle 100% depth of discharge is probably the areas where that we're still working hard on. Recharge time. Our 6 amp hour cell, which is where we've done all the independent performance testing. So let me say this, all the results that I'm showing today are not just, hey, believe my beautiful PowerPoint. We give out hardware and OEMs test it and they believe it or they test for themselves. But we also have done independent third-party performance and independent third-party safety testing. First thing I want to tell you is that we have, in that independent third-party stuff, we've demonstrated 15-minute recharge capability. But what I'll show you is that in our labs, we've demonstrated as fast as 8-minute recharge, which I think is as fast or faster than anything that I've seen. Some of the silicon anode guys have touted 5 minutes, but I'm not going to quibble. It's when you're at this kind of a fast charge rate, it's almost equivalent to pumping a tank of gas. What is the issue with fast charge tends to be degradation. And what I'm showing here is that we are doing 15-minute recharge with alternating regular charges and fast charges. And I think we're up to about 400 cycles now. So this one's a little bit out of date. I will tell you, if you do every cycle at 8 or 15-minute recharge, the lifetime probably degrades by 60%. So fast charging is an issue, but if you do fast charging occasionally, there's no degradation at all. So, I mean, how many people really need the 15-minute or 8-minute recharge every day? Our grid can't handle that. And in fact, you'll probably pay for the cost of electricity. You'll probably pay through the nose if you do that. But if you're taking the family on a cross-country trip, from time to time, you need to quick charge. And our technology can handle that. So we're very excited about that. Just not too many more slides. We can take a bunch of questions if you guys like. We have a liquid electrolyte. And frankly speaking, that's the, what's the secret sauce? How do you get cold temperature operation? We're not using solid state. We're using liquid, and we have very good cold temperature performance. This is the slide that I'm saying we have done independent third-party performance testing on our 6 amp hour. And I'm not using one design for energy and one design for cycle life. The same battery was tested for energy, power, fast charge, cycle life, temperature performance, abuse. And in fact, I would say we've also done a great deal of safety testing. People have been skeptical about lithium metal anodes. Can you do them safely? And what I'll tell you is we're the first high energy product that is past UN DOT 38.3. Everybody will have to do it in order to be able to transport their batteries. But I'll say we have comparable safety to lithium ion. Not better, but not worse. And one of the things that's allowed that to happen, some companies talk about they have monitors for determining if dendrites form. We don't allow the dendrites to form. Part of that is a redundant cell design. The first one is our lithium metal anode has a physical barrier. So you could think of it as ceramic on top of the lithium. It works. We also have chemical protection, meaning additives to the electrolyte that inhibit dendrite growth. And finally, 2 levels of pack protection. The first is compression. That, if you know lithium ion and you know nickel metal hydride and you look at modules using pouches and prismatics, there's a certain amount of compression that comes from the module having end plates. That compression, we use 3 times more compression than regular lithium anode, and that works. The BMS also controls it. So here's the bottom line I want to give you the takeaway. We don't allow dendrites to form. We don't allow mossy lithium to form. And if you do that, you don't need a solid state separator to block the dendrites. So the companies that are trying to say dendrites will form, there's nothing you can do about that, but we're going to block it. We take a different approach. Never let them form. And then you can use existing lithium ion, everything else. And what the message I want to give you here is that if we look at the thermal behavior for our technology, the cathode has more to do with the thermal behavior than the anode. So as we go higher in nickel concentration, the runaway temperatures are directly affected. An LFP cathode, on the other hand, would be very similar to lithium ion. Think about it. If you got something with 300 watt-hour per kilogram and another system with 300 watt-hour per kilogram, that energy needs to be released at some point. Last thing, and then we'll close for tonight. The last thing is the ease of retrofit. how would you like to have a new battery chemistry and tell the people that have invested billions of dollars in gigafactories, hey, scrap that if you want to make our technology? The first message is 80% of an existing lithium ion factory can be retrofitted to make Licerion. We do scrap the graphite. There's nothing I can do about that. And we replace it with metallic lithium anode, but everything else stays the same. So our business model is we're going to supply the lithium metal anode to existing lithium ion companies and let them transition from graphite to Licerion. And so we think that's from a business perspective, that's a capital light model where we're not going to build the battery factories ourselves. We're going to take advantage of the infrastructure for the automotive companies, the guys you're buying batteries from now. You'll still buy from them. They'll just substitute the graphite with lithium metal anode. So it's really my pleasure to talk to you guys tonight, and hope this was interesting. And I'm happy to take questions if you like.
Great. Chris,
Great.
did you want to do this?
Yep. Let
Yep,
me open up the chat again since it just moved on me. Okay, so first question is from Tobias. Do you know if LFP patent enforcement could have changed its path as it did for NMC?
I think the key patents, because the BASF was a licensee of Hydro-Quebec for LFP cathodes, and the key patents, to my understanding, I guess I should say I haven't taken a look at this in a while, but as far as I know, the key patents have now expired for LFP, and that's one of the reasons that LFP is beginning to proliferate again. But you know, there's always can be new things that happen. But I think LFP patent enforcement, the patent terms, the license and the royalty terms were odorous, and I would say that when those patents were in play, it did inhibit some of the use of LFP. Now that the patents are expired, gee, what a coincidence! Now the use of LFP is beginning to heat up again. I think that's also, though, it's not just the expiration of the LFP patents, but the concern over the cobalt and nickel availability is also causing companies to want to have an insurance policy, or maybe they have a marketing strategy where they've got some mainstream entry vehicles, and maybe they've got some premium, more higher priced cars. I think all of those things probably combine on that question.
Yeah, Chris, I guess I could have read my own question. I didn't realize my
Sorry,
first
I'm
question.
looking
You can read your second one if you'd like.
Yeah. So I'm also curious about the manganese rich high energy NCM. I'm aware of the material, but what is your perspective on that? How far away is that from that you can just buy it tons from suppliers?
Place an order. I think the NCM 307 is unique product to BASF right now. And I think I would say the cycle life is not exactly as good yet as as regular NCM. And I would say maybe high temperature conditions. So I don't know that I would use 307 in NCM 307 in Phoenix in the summer on asphalt. But maybe it's not perfect yet, but it's getting better and better.
Yeah, so it could be tuned to the application also by the material manufacturer. Okay.
Absolutely. And surprisingly enough, it's not just the microstructure of the material and the electrolyte, it's a system, but the BMS has some influence on the performance of the 307 material also.
Oh, we're good at BMS and the car companies.
So I think a combination of somebody like BASF Cathode with a company that's willing to work together with them to, not only the application should be tailored, but the the pack and the pack and the construction also, if that's all done, I think the stuff is, I think it's
Right.
ready to go.
Awesome. Thank you.
Okay, let's see, I can scroll down, so Ankun.
Or you guys, you can also, if you want to read your own question, you can unmute yourself too. I think we have a meeting set up that allows us to have everyone to interact with each other. So it's great.
So Ankun, did I already answer the lithium dendrite question, or do you have any follow-up?
Yeah, thank you for the nice presentation. Yeah, so you touched, I mean, yeah, basically you answered that, but I don't know how far you can go into that details, like how you are able to basically not allowing the dendrites to grow, because as far as I know, the dendrites are very strong. They can penetrate even like strong ceramics in the solid state studies. So that's something that I don't know how far, details you can
We'll
talk
be
about.
publishing some more of that information in the future, and we're also working with Shirley Meng from Argon and
Yeah, I know.
San Diego, and Shirley was interested in some of those same questions, and I think she wants to publish some papers where she's been, I think, totally surprised pleasantly by how well we've done on this topic. So the combination, Ankun, of compression, electrolyte additives, and what we call, it's not just lithium metal anode, what we call a protected lithium metal anode, where the ceramic barrier that we put on top of it, the combination of those three things is very effective.
All right. Okay, thank you. So can I just maybe finish I have several questions. Maybe I just go quickly, if that's okay.
Sure.
So how thin the lithium metal you can put in that, vapor deposition approach?
Yeah, we started out, our designs 3 years ago, we're using 30 micron foil. But when we do the vapor deposition, it's 15 microns now, and we'll be going to 5 microns. So this is a vapor deposition. Think of it, the way I tell it to lay people is, if you open up a bag of potato chips and you see the inner coating of the plastic, it's an aluminized metal coating on plastic. Think of that as the way we do the lithium metal, and it's that thin.
That's thinner than the separator right now, right?
Yeah.
Okay.
We don't want to use more excess lithium than we have to for cost reasons. So when we have an optimized design, I expect it to be 5 microns, 8 microns, something like that.
All right. Okay. Thank you. So the final question I have, if you have time later, maybe after addressing others, so is that I hope that you can share with us a little bit more about the next after the lithium metals, in particular, what cathode material you would think that are competitive. And particularly, I want personally, because I'm interested in sulfur chemistry, so I want to hear your comments on the sulfur cathode in particular. Thank you.
You're welcome. That's a great question. We're going higher and higher nickel for energy, but we're also scrapping nickel entirely and using LFP for some designs where people weigh cost and safety versus energy. But I still love our sulfur cathode. Frankly, we're not doing too much work in that now, just so we're not distracted. But watt hour per kilogram for sulfur and the cost are fantastic. So first, the two concerns with sulfur, there's only two. One is watt hours per liter. So when we go up from 300 to 400 to 500 watt hours per kilogram, the watt hours per liter is not great for a car where volume is just as important as weight. But if you have an application that is not volume dependent, fantastic. Sulfur could be a fantastic choice even early. but cycle life is still not there. So under the same conditions that I get 2000 cycles with a nickel cathode, I get 500 with sulfur. So I don't, for some applications, again, that might be perfectly adequate. And I will tell you for aerospace, weight is important, volume is not, cycle life is not so critical. So I think lithium sulfur will be back in the market starting with aerospace applications at some point. That's my opinion.
Thank you very much.
Where are we at on the next?
Yep. So
How
next,
should I do the
next
question?
question. Sorry, what?
How should I do the questions? What order or?
So the next one's actually from me. But basically my question is how does calendar life of these lithium anode cells compare to like a conventional graphite, since there's not really necessarily an SCI layer there? Maybe there is, but I mean, is there something there to sort of slow down that reduction reaction?
We think it's comparable to it's a good question where I have to sometimes say, I find in the industry, one of the annoyances is when the true answer is, I don't know. People don't want to say, I don't know. And because we haven't had batteries in the field for 20 years, I have a tough time projecting 20 years, but we think comparable calendar life to lithium ion. And partially I give you that answer because, you know, at BASF, I was very active in failure analysis of lithium ion batteries. And a lot of the calendar life failures of lithium ion were cathode related. Leaching of manganese, SEI layer impedance buildup at the cathode. And so to the extent that the cathode controls a lot of what calendar life is determined anyway, I would say similar, but our SEI layer is stable. And so right now, the best we can say for now is similar calendar life to lithium ion.
Thanks.
When Tobias questioned, you know, he was asking about the 307. Maybe that would be, you know, when I talk about that material, is it ready yet? Maybe not cycle life, but also high temperature stability. That 307 material, I would be dubious if that one had the same calendar life as a 622.
Yeah, so it probably behaves somewhat similar like an LMO.
Yeah, well, in some of the LMOs, I think there could be a resurgence of LMO too. And a lot of people working on those things, maybe stabilizing agents. You know, you couldn't have used silicon in the anode a few years back either, because people are doing some wonderful silicon work. The Innovate company with, you know, with these super lattices and people using structures that can help keep the silicon stable. It's exciting to see. And I think a material like LMO, there's people with good ideas on how to make it more conductive, how to make it more stable. And so, you know, I'm interested. I think it's horrible when somebody says, oh, we tried that 10 years ago, that'll never work. Doesn't mean it won't work again, but it'll require fundamental material advances, in my opinion. But there's so much effort by so many smart people on exactly these subjects. I don't want to say it can't be done. Nickel metal hydride couldn't be done until we did it. And I think NCM cathode couldn't be done until it was done. And so Mike Thackeray, a guy like that, took a material that wasn't working, could never work, and made it work. And so if people come up with new breakthroughs on the material science, I would think LMO could make a comeback as well.
Okay, thanks. So the next question is from, on the list, is from Aniko. I think that's how you pronounce the name. Aniko, did you want to ask your question, or I guess?
Oh, I see it now. So, okay, it's the how stable the lithium metal vapor deposition process does it require an inert atmosphere? Okay, so we make the lithium metal anode today using vapor deposition. Inside it is a vacuum, but people outside the machine are standing there in air. when we do take the foil, so the lithium vapor deposited material that's on a roll to roll, we transport it in an inert environment to a dry room. So what's important is just humidity control, the same way you already do when you make lithium ion batteries. So we don't need an inert environment, but we do need a humidity or a dry room atmosphere for handling the lithium metal anode. But it's people say it's reactive. Yes, it is during the process. So we're using not an ultra high vacuum, but we do use a vacuum process similar to it's. I would say vacuum deposition is not so common in the battery industry, but it is common in solar. It is common in semiconductor. And we believe, I guess I didn't touch on this earlier, we believe our Licerion technology will be the same cost as lithium ion. So even though we're using a vacuum deposition process, it is it's new to the battery industry, but it's not new. Let me say it that way, and can be cost effective with regular lithium ion. Let me see, I'm scrolling down. We did Ankun, Gongshin.
So I think the next one is, yeah, the Gongshin.
SES. Well, it's never, when somebody's doing R&D, you're not quite sure what they're doing, but we understand SES is using lithium metal anode. We understand they used to be called Solid Energy. They changed their name to SES at the same time. I think that they went from a solid electrolyte to a gel or a liquid. So in some respects, they look similar. SES seems to be taking the approach that they're not preventing lithium dendrites there, but they're detecting when they form. They have, I'm not sure, I don't want to speak on behalf of them, but I think we've been using lithium metal anodes for decades now, and I think we have a very strong patent position. I believe anyone that markets or commercializes a battery with lithium metal anode is probably going to need a license. So SES, we probably would be talking to them at some point. I guess they'll need patent access, but when somebody's doing R&D and development, that's fine. When it becomes commercial, we'll take a look and see if there's a problem or not. Okay, then I see Amit, withstanding such high rates. We have demonstrated in our large format design 8-minute recharge. So that's not a projection, we've done it. So that by definition, that says that the rate capability is high enough to handle that. Is there polarization? No, well, in regular lithium ion, there is more polarization. Let me say it this way. It's much easier to quickly recharge lithium metal than it is to recharge lithium in graphite. So the way we can do 8-minute recharge is because we're using lithium metal anode. It's the graphite anode which inhibits the rate at which you can recharge regular lithium ion. If you do recharge lithium ion, charging lithium into graphite, and you go too fast, that's when lithium ion forms dendrites. That's when lithium ion degrades the SEI layer. So our methods of preventing dendrites from forming are part of the reason that we can charge so fast.
So just sort of a quick follow-up question to that. So with your technology then, there's no charge transfer resistance or solid state diffusivity then on the lithium then, right? So you don't really have that type of polarization?
Yes.
So really when it comes to your charge rates, you're mostly then just going to be limited by what your cathode can do and then your electrolyte then, right? It kind of takes the anode out of the equation.
Kind of.
Okay.
There's some polarization, but it's small compared to the two other items you already mentioned. So we're not geniuses on fast charge. Lithium metal anode enables much higher charge rates than you would be able to get from graphite. Now, some of the silicon guys, Ben Park and the Innovate guys, are touting 5-minute recharge, and I saw them a few years ago, and I believe that they can do that. I mean, that's their design is emphasizing fast charge. Maybe it's not as high of energy as other approaches for using silicon, but will there be markets for ultra fast charge? Absolutely. So I think the market is so vast. Consumer is still significant, grid storage, all kinds of EV applications, trucks, motorcycles, boats, you name it. Some of the people working here, I saw American Battery Solutions talking about their technology for boats. The market is growing at such a high rate. I don't think we're competing with those kind of approaches. I think there's room for everybody to do very, very well. And there'll be some market specialization. What I don't want Sion to be, I don't want us to be a niche technology. I want us to have a huge market share. And I think that'll be determined by how quickly we can ramp up our production capacity. And then I have to admit, we're at pilot level right now. So when a guy like me is talking about at scale costs comparable to lithium ion, until you prove it, you have to say there's some, well, you need to demonstrate that, don't you, Mike? And I would say, yes, we do. How quickly we're able to prove out our cost compared to regular lithium ion, I think will determine how big our market share is by what time. I think it'll be that simple for us. And I think other companies have similar challenges, but some companies are really scrambling for funding. And, from time to time, people might exaggerate their projections and things like that. So you have to take what everybody says with a grain of salt. And that's why I say, don't believe the presentations, and certainly don't make decisions based on PowerPoints. Get samples, test hardware, and make up your own minds. And I think that's what our partners have done. Everybody is happy to see your third-party independent testing, but they are also skeptical enough that most everybody wants to do their own internal testing in-house to verify. That's just the way of the world. I think. There's another question from Ryan. How would you predict? So we're at pilot level right now. We can make a few dozen batteries a day. We're setting up right now a 74 megawatt hour pilot plant, and we're raising money right now to do that through private rounds. We're probably going to go public at some point, and we'll be trying to raise 600 million or something like that to set up the next generation. But let me say it this way, Ryan, it's a great question. Once we set up the 74 megawatt hour pilot facility, that'll make batteries. After that, our expansion won't be battery production. It'll be anode production that then gets shipped to battery companies that would be, let's say, tier 1 suppliers that would take their existing lithium ion factory and retrofit it to make Licerion. So you could imagine, let's just use an example, LG in Holland, where they make lithium ion today with graphite anode. Maybe they would continue making graphite anode for 90% of their production, but maybe they would introduce lithium metal anode for a certain portion of their production, get more comfortable with it, and gradually increase the amount of lithium metal anode production. That's the way I envision our commercialization to happen. Now, when I used LG, it was as a representative example, not that there's anything in place with them. Okay, Ryan seems satisfied. I don't know if I see additional questions, but I guess I'll look at Chris and Eric and Tobias if you want to keep going, or is everybody exhausted, and maybe see what's on HBO or.
Yeah, well, I think it's almost 1:30 a.m. for Tobias, so I think he might be done, but Eric, did you have any final words or comments before we adjourn?
No, I think we captured most of the questions. I guess just one quick comment. I can again bring up the election. So if anybody missed it at the beginning, we are going to have the ECS elections for our chapter, but we're going to do that by email. So just be on the lookout for some emails from us, and then a corresponding link to SurveyMonkey to vote on the members for the section this year. So, but yeah, with that, I think we're pretty much wrapped up. So thanks again, Mike, for taking the time. Obviously, it was a very interesting presentation, especially going through the whole history from nickel metal hydride and how you got to kind of where you are. So thanks again for volunteering.
As the Grateful Dead said, it's a long, strange trip it's been. Have a good night, everybody. Thank you.
Yeah, thanks.
Thank you.
Take care,
Thanks a lot,
everybody.
Mike.
Thanks again for joining.
Thank you very much.
Bye.